All right, class, I got some good news and I got some bad news. Bad news, obviously, we got a video to watch and some notes to take for Monday. The good news is that'll mean a lot less notes to be taken in class next week. And I also would say some good news would be those of you that suffer ADD like myself, most of the good information is coming at the beginning. The examples are actually pretty straightforward. You just got to learn some vocabulary and some different situations that arrive. As you can see, we're working on Unit 5, Systems of Linear Equations and Inequalities. That picture right there gives you a good idea of what's coming, especially today. The essential questions will also kind of guide you as we go through Unit 5. It should be a shorter unit, should be a quicker unit, and should also rely a lot on your background knowledge, especially as we begin today. Essential questions, how many solutions are possible when solving systems of equations and inequalities? We'll actually be able to answer most of that question today. What 3 methods can be used to solve systems of linear equations? Again, we'll answer what those methods are today. You'll learn those 3 different methods over the course of the next couple weeks. And then how can we use linear systems to solve for multiple unknowns in real life situations? Nice thing about systems of equations, now we can have more than one unknown and still be able to solve for that. So that kind of sets the table for the next few weeks in Unit 5 with linear systems. Today specifically, we'll get started with Part 1, which is just graphing, which again, that picture really provides you a good idea of what's happening today. Pretty simple, actually. We're going to graph, and we're going to use it to solve some systems of linear equations. Before we can do that, you need to know some things about systems of linear equations. A system of linear equations, or linear system for short, it consists of 2 or more linear equations with the same variables. Most of our systems will consist of exactly 2, but we can have more than two different equations. Now, it has to have at least 2, otherwise it's not a system, we just have a singular equation. The other key here that is important not to forget is they have to have the same variables. Now, that's pretty obvious when we're dealing with things like x and y. Those are the 2 most basic variables that we look at. But when we get into the real life situations, we got to make sure that we're talking about the same unknowns, whether it's an independent or dependent. We got to make sure we're talking about those same variables in each of our situations so that we can write equations and put them into a system. A solution of a linear system then is an ordered pair that is the solution of each equation in the system. Basically what that means is if I can find an ordered pair that works for all my equations, then that would be the solution for the system of equations. If it only works for one of the equations, it's not a solution in the system. It's just a solution of that equation. That brings up an interesting question as far as what determines if we have a solution or not in our system and how many solutions there can be. Notice it says a linear system has a solution at each point where the graphs of the equations in the system intersect. Now, we're going to work on graphing today, but that doesn't necessarily mean that's the only way to solve these systems, and we'll see the other methods that we can use to solve these systems. When we're working with this, though, we should get an idea of, okay, if it's at every point that they intersect, there's a certain number of solutions that we can have. And there's actually 3 different situations that can come up. We'll talk about all 3, and we'll see all 3 this week. Think to yourself a little bit, how many solutions are possible for a system of linear equations if it has to do with intersection points? Hopefully that was enough time. Hopefully you paused the video. Hopefully you got a lot of think time in. There's 3 different situations that come up. We'll start with the first, maybe sort of common. The most common will be our second. First situation that can come up is we have no solution. If we would have no solution, that would mean that the lines are parallel. And if we have 2 parallel lines, or 3 parallel lines, we know they will never intersect. They have the same slope but a different y-intercept. They'll never intersect, and if they never intersect, we have no solution. And so that's one situation that can come up. We can have no solutions. We can have 0 solutions. Because there's no solution, because this system doesn't work, because we can't come up with a solution, we consider solutions that have, we consider systems that have no solution to be inconsistent. They're inconsistent with what we're used to because they don't have any solution. The second situation that come up is the most common. It's pictured right here, and it's also pictured on the title slide that we started. What we typically have, they intersect at one point. That point becomes our solution. If lines are not parallel, by definition, they must intersect at some point. And so we know that we would have a solution of some type. Wherever they intersect, that would be our solution. If you can use some deductive reasoning and synthesize this idea, this system would be considered blank and independent. Well, if no solution is inconsistent, this system would be considered consistent. It's consistent because we have a solution, and it's independent because those 2 lines are independent of each other. They do not rely on each other. They are not the same line, hint, hint for our next situation. And so they just have the one solution and they're independent. Now, we could have no solution, we could have one solution, and we could have more than one solution. But I want you to think about how we could have more than one solution if the solutions depend on where they intersect. If we have straight lines and they intersect at more than one point, They can't just intersect at 2 or 3 points. That means if they intersect at more than 1 point, they actually intersect at all the points on that line. We can have infinitely many solutions if the lines in a system are the exact same line, same slope, same y-intercept. This means they have infinitely many points of intersection because they're right on top of each other, and that means they have infinitely many solutions. Because of this system is considered consistent because it has solutions, just like with our previous example. But now, because they're the exact same line, they have the same slope, and they have the same y-intercept, we consider these to be dependent systems. They're consistent and dependent because those two lines depend on each other. For those of you people that are visual, I think this is a really good shortcut, really handy to have in your notes, especially for a journal coming up on Wednesday. But it kind of gives you the 3 different situations that can arrive. We see that we have no solution. We have an inconsistent system because those two lines are parallel. That would be the first situation that we have. Then we have 2 different types of consistent systems. The first one would be when we have independent systems where we have exactly 1 solution, 1 intersection point. The other consistent system that we would have would be a dependent system because they are the exact same line and we have infinitely many solutions. Now, where we want to go from here then is, well, how do we solve these systems? How do we find these solutions? There's 3 different methods that we will work through in Unit 5. The first one we'll cover today. The other 2 will come down the road. As you see, we can use graphing, substitution, and elimination. Graphing, the problem there is it's the least reliable and it does not work for all systems. If you think about it and you think about what solutions are possible, I think you could come up with why graphing is a little bit difficult. Substitution is a little bit like it sounds. It's best if one linear equation can be easily solved for one of the variables. If we can solve for that variable and substitute it into the other equation, we can solve from there. And then elimination actually works where we do eliminate one or the other variable. And you'll see what that means here in a week or 2. So to solve by graphing, it is simple. It's not reliable, but it isn't necessarily reliable, but it is simple. Graph the equations, identify the intersection point, and then double check it and make sure that that is your intersection point and that is your answer by substituting it into each equation, just to double check and make sure that you were correct. An example right here would be this system of equations. We have 2 equations, y equals 2x minus 4, and y equals a negative 3x plus 1. I'll begin with that first equation. I want to identify the slope and the y-intercept. It's nice because they're both in slope-intercept form. I can start at the y-intercept like we've been taught, and I'm going to go up 2 over 1 because the slope is a positive 2. I can do the same thing back the other way. Like we've talked before, really want to try to fill the graph. Man, that's a nice straight line. You are welcome. Really want to fill the graph so we can see these possible intersection points and identify what it might be. Again, identify the m and the b. Start at the y-intercept. This slope is a negative, so it would go down 3 over 1. It looks like we may have found our possible solution, but we're going to double check it. Finish out graphing. Don't forget to connect the dots, draw the arrows, another straight line. You guys are lucky to have such a spectacular math teacher. Identify that apparent point of intersection. It looks like the x value would be 1 and the y value would be a negative 2. Not done yet. Want to check it in both of our equations. We'll check it in the first equation by substituting. That means I'd put a negative 2 in for y and a 1 in for x, and I'd check this out, and it would look like negative 2 does in fact equal 2 minus 4 because that's also a negative 2. So that seems to work in that equation. I want to go back and check it into the other equation, checking into the second one. I'm putting y in for y, so I would have a negative 2 equals negative 3, 1 in for x, plus 1, and you see that negative 2 does equal a negative 3 plus 1, and they both do check out and they both do work. That takes you back to your answer. Your answer for this system, we would have a consistent independent system because we have 1 solution at the ordered pair, 1 negative 2. One example for you to do on your own before Monday, again, just solving it by graphing. I want to graph these 2 equations. One thing that I would point out, this equation looks a little different than what we're used to. Might want to get that into slope-intercept form, and I think it's actually a pretty quick fix to do that using some of the background knowledge that we've got from algebra. So again, important information that came to you today. We did discuss the 3 different methods for solving. We've actually now gone over 1. The other 2 will come. And then, of course, we really talked about the different situations that can arise when we're solving linear systems. We can have 1 solution, no solution, or infinitely many solutions. And again, a little visual aid to help you with that. That takes care of part 1 of solving linear systems. You should now be able to solve linear systems by graphing, and you should have a really nice base for starting out Unit 5.